Okay. It is a great pleasure to introduce Atilla Yurdakul. Atilla is a rising third-year student at Galatasaray University Department of Mathematics. He will talk about, the University, I'm sorry, the University Department of Mathematics. Today he will talk about one of the simplest, yet one of the most important models in the realm of topological phases of matter, the Toric Code. Atilla, the stage is yours.
Thank you. Hello, everyone. Today we will do a brief introduction to the Toric Code.
Tamam, yanındaki şeyini açmamız lazım. Deneyebiliriz.
Okay, we will do a brief introduction to the Toric Code. We will talk about the topological phase, a square lattice, and the Hamiltonian of the system, which gives the total energy of the system, the ground states, excitations, and cross particles. Şunu aşağı indirsek olur mu acaba? Çünkü başlıklar gözükmüyor. Okay. We begin with defining the topological phase. And we say that there is a topological phase if there is an energy gap between the ground state and the state after the ground state, like the first excited state. If there is a finite energy gap between those, we say that there is it is a topological phase. And we will show that by excitation, there exist onions which act like also fermions and bosons at the same time. And the Toric code is defined on a two-dimensional square lattice with the spin 1/2. And this means that on each edge, the squares show that there is a spin placed on every edge. And these are the plaquette and the star operators that we will define later. Okay. And spin 1/2 means that each spin is represented by a two-dimensional vector, and we can also say that each spin is represented as a linear combination of spin down and spin up. And the total energy of these physical systems is defined by this, is given by this Hamiltonian, where these are the star and plaquette operators, and S and the P are the stars and plaquettes. These are stars and these are the plaquettes. So we define these operators as follows: as the product of sigma x and sigma z's, where sigma x is this Pauli matrix and sigma z is also the Pauli matrix. And observe that the eigenvalues of the stars and the plaquettes are both plus and minus 1. And now we come to the ground state. The ground state is the state which the system as it is at lowest energy level. We want to find the ground state because we are able to build all these excited states over this ground state. And quantum computation is being done over these ground states. To find the ground state, we will make some observations and use a postulate from quantum mechanics. And the postulate is this: observable quantities must be the eigenvalues of the quantum mechanical operators. Therefore, to find the ground state, we need to find the eigenvalues of the Hamiltonian operator. And to find this, we will use a theorem from linear algebra, and the theorem is as follows: a set of diagonalizable matrices commutes if and only if the matrices are simultaneously diagonalizable. So we will show that all the elements of the Hamiltonian commute. It suffices to show all the elements of the Hamiltonian commute. And the elements of the Hamiltonian are the placket and star operators. So we are going to show star operators and the placket operators commute. If star and placket do not share a common edge, then they obviously commute, since they are being validated on separate areas. But if they share common edges, then the edges being shared is an even number. And also observe that sigma x times sigma z is equals minus sigma z times sigma x. So they anti-commute. But since they intersect at even number of edges, the minus will disappear. Now by using our theorem that we have stated, diagonalizable matrices theorem, we can diagonalize all the elements of the Hamiltonian at the same time, and we can solve that. To minimize the Hamiltonian, the eigenvalues must be +1. Now, since we have found the ground state, we come to the fermions and bosons. In three-dimensional systems, there exist two types of particles, fermions and bosons. Bosons, when we interchange the positions of the bosons, when we take two bosons and we interchange the positions, the state of the bosons stay the same. But the state of fermions changes. It gets a minus sign. So now keep in mind that. And this is because of the Pauli exclusion principle. Now, to find the excitations, the states can be excited. And to find these excitations, we define two types of operators. The one is which finds the electric charges, and this is called electric path operator. And the other one is called dual path operator, which finds magnetic vortices. The electric path operator is defined as this, and it's being validated on L, and L is the path connecting 2 points, S1 to S2, and these 2 points will become fermions later. Okay. And this is the path, this is the L. It cannot be seen from here. Okay, this is the path connecting S1 to SL. And we are exciting the state with sigma z's. And we will study how it behaves. But first, we will show that. Well, we will not explicitly show that, but we will be able to see that this electric charge operator commutes with the placket operator, since sigma z commutes. We also know that sigma z anti-commutes with this star operator, since it intersects with the star operator once. Therefore, if psi is an excited state by sigma 1, sigma 2, and sigma 3, as shown here, then when we apply the Hamiltonian, so when we want to find the energy of the system, this equals to E times psi, where E is an eigenvalue of HD by our facts, by our postulate of the quantum mechanics. But we also have Hamiltonian equals to this when we write it explicitly, because we have excited the state into sigma 1, sigma 2, and sigma 3. By separating the operators on S1 and S2, we define the high prime, H prime, and when we apply it to psi, we get this. By combining all, we get this, which gives us this. And what does this mean? Remember when we talked about the topological phase, we wanted to show that there is an energy gap between this state. We can come back to the first slide. We wanted to show that there is this energy gap between the ground state and the state after it. So we have done it by showing that there exists a 4G sub A of energy difference between the ground state and the state after it. A similar construction is followed when we define the electric, when we define the dual path operator, which finds the magnetic vertices. We will come back to grades later. We have time. Okay. When we try to illustrate this grading model, which we will talk about later, on the Toric code, so what we will do is take an E particle, which is done by exciting the state with this electric path operator, and when we travel around the end like this, when we travel it's around the end, as I shown, we will study how does it behave. But I should say that in the first hand, the particle E and M act like fermions. When we take this E instead of M, the status does not change. So we will not get a minus sign, which is a behavior of the bosons. But when we do the same thing with the M's, when we take two M's, the state stays the same, just like bosons. But when we take this E and take this M, we will get a behavior like the fermions. How do we get this? Let's see the state shown in the figure like this. We take it and travel it around the M. When we apply the full grading operation, which changes the position, and the C is equal to this. This is a Stokes theorem like result, because when we travel it around this, it is equivalent to evaluating each one in the plaquettes. So the state C is equal to plaquettes times C. And since there is a vertex at P1, this means that there is a vertex at P1. The plaquette operator gives us a minus. So the state C is equal to minus C, which is the behavior of the fermions. So these E and M altogether act like fermions. But if they are single, they act like fermions. They act like bosons. And we call these as Toric particles. There is two more operators in the Toric code. And when we consider the torus, the word toric comes from the torus, because we define all these lattices on the torus. These are embedded into a torus. And we have two more operations in the Toric code. And the one is which, when we apply sigma d vertically, I should come back. And the one is which we apply sigma d vertically to the torus such that it grabs the closed pole of the torus. We can observe that this operation commutes. This operation commutes with the bracket operator since sigma z is commutes. But we can also see that this operator commutes with the star operator, with the AS, since it wraps the closed hole, and when we apply stars, we will have two edges. We will have two edges intersecting with this operator. So we will have again two minus signs, which will cancel each other. So operator also commutes with all other operators. And the other operator is that when we apply, the other operator is generating by applying sigma z's horizontally on the torus. And because of the same reasons, this also commutes with all other operators. But now we have four ground states. Because of the reason that these vertical and horizontal operators have two eigenvalues, which are plus and minus 1. So our ground states are the ground states that we have found, and 0 minus 1 minus 1, and the ground state minus 1 plus 1, and the ground state 1 minus 1, and the state ground state 1 and 1. And between each of the operators, there is this 4GA energy gap that we have found. Because of this reason, these results are being used in the quantum computation, and this is called a fault tolerant code because there is a 4G sub A of energy gap. Okay, thank you for listening. Any questions?